multiplication rule applied for multiple events, right? One of the most common questions I get when it comes to probability, after the statement of probability is so hard and I hate it, right? Then the questions come in. How do I know the difference between the addition rule and the multiplication rule? How do I know when to add and when to multiply? Right? Multiplication rule, multiple events. If you have only one event, you're not going to be multiplying anything. Right? In the previous case, in those previous problems that we were working on, it was one card being selected from a deck. Now, all these possibilities came into play. It could be a 7, it could be a red card, not a red card, all that other stuff. But it was still one single card being selected at random. Now we have 2 cards being selected at random. And later on in the unit, we'll talk about what happens if you're selecting more than 2. You know, because if I'm, interested in games of chance, I might be thinking, okay, well, 2 cards being selected, that sounds useful, but what if I want to play a little poker, and I'm selecting 5 cards? I want to start getting into those probabilities. How's that going to work? We're getting there, and it's an interesting experience. There's a lot of variables when it comes to poker, not the least of which has to do with the human element. So a lot of good stuff to talk about down the line. But anyway, 2 cards of the same suit. Again, 2 cards are drawn from a standard 52 card deck. The first one is not replaced before the second one is selected. We want to know that they're 2 cards of the same suit. Right. So again, the suits, and this is where my my glorious drawing ability comes into play. So the suits are diamonds, hearts. I almost drew something else. I was trying to make it into a spade or something. I don't even know. But it wasn't going well. There's my spade. And then that's the best I've ever been able to do for a club. Looks like a Smurf giving the middle finger. Yeah, that's all I got. So we're looking at 2 cards of the same suit. That's the multiple events. So therefore, multiplication rule. Okay. So we have a little bit of uncertainty here, because you say 2 cards of the same suit, and the response might be, well, which suit are we talking about? And the answer to that is, well, any of them. So what I would have to do is I'd have to account for each possible way we could have 2 cards of the same suit. So we might have a heart and a heart. I'll do it in the order that I drew the diagram. A diamond and a diamond. Yeah, we might have, I'm just going to get my setup here. Get my ampersands. A heart and a heart. A spade and a spade. Oh boy. And you don't have to draw the diagrams. Although if you can draw them nicely, it does bring like a little smile on my face when I'm grading people's papers, because I always do kind of get a little bit of joy out of seeing the fact that there are people out there that can actually draw, so. But yeah, you could do C for clubs and S for spade. You know the drill. Not the drill. So the way we would evaluate this in terms of probabilities would be to say, and this is where it gets a little funky, probability of a diamond multiplied by the probability of a diamond given that the first card selected was a diamond. Right, that's that notation that we were talking about last time. You can get away without using the notation, but you really can't get away without recognizing the notation. Like you don't have to actually use the notation yourself in order to come up with the answer, but in order to kind of understand other people's work, that notation is going to crop up from time to time. So you see in blue above for number 1, where it says probability that the card selected is an ace, given that the previous card selected was a king. Replace ace and king with diamond, and you have the same idea, right? So what this means is the probability, and you know what, I am going to write it because I was debating whether or not I would, but I'll write it. So the probability that the card selected was a diamond, given that the previous one selected was a diamond. Writing a little bit more shorthand here though. Previous was diamond. And you might kind of look at it like, oh, what's the deal with this notation? Why are you harping on the notation? Personal experience slash hatred. Because when I was at, I think it was my senior year, maybe it was my late junior year at NYU. I forget what teacher I had previous, if it was high school or whatever. They didn't harp on notation at all when it came to probability. But then in my senior year, late junior year, I was taking a probability theory course at NYU, and they and the professor there, I'll never forget his name, Professor Greenleaf. There's nothing special about him, in my opinion. It's just his last name was Greenleaf, so I just remember that. But anyway, he hit the ground running in the course, talking with his only vocabulary being the notation and language of probability. So everything that went up on the board, chalkboard at that time, was written along these lines. And coming from a background where notation was not emphasized at all, like I don't even remember who taught me probability along the way in high school or whatever. And even if I did, it would have been so long ago that it wouldn't necessarily kind of stick out, but it was like Regents level kind of stuff. Notation was not emphasized. So when I saw this, it was like, what is going on here? So that's why I'm taking the time and really kind of emphasizing what the notation means, because I don't know where everybody's going to end up after this. For some of us, this is the last stop. No more math after this. Yay. Boo, depending on your feelings about math. But
yeah, that's me.
That's you, exactly. So, but there are some people that are going to have to take follow-on classes to this. So, this is Intro to Probability. That part of this course is Intro to Probability. You might take a probability theory course. You might take a stat for biostat class, an engineering stat class, a math stat class, all sorts of possibilities where probability will come up and you don't know who you're going to get. And when you get those individuals who just love that notation, sometimes they just expect you to know it and they're not going to stop. So that's a little word on why I've kind of forced the issue here. So there are 13 cards in a deck that are diamonds out of 52 in total. All right. So that accounts for this first element here. Then what we do is we multiply that by the probability of getting another diamond, given that the first one selected was a diamond, right? So conceptually, it's not too bad, because what you're doing is you're imagining a well-shuffled deck of cards. You selected a card at random. We always assume success with probability, right? So we're always assuming success. We got the diamond. All right, I got one diamond, one step towards a flush if you're thinking in terms of poker. All right, so now I toss that card. It's not going back in the deck. Shuffle the remaining cards up, draw another card at random. There's 51 cards available. But now there's only 12 that are diamonds. All right, because the first card selected was a diamond, or the previous card selected was a diamond, the probability of getting another diamond, I have less diamonds to play off of here. All right, so again, there's 4 suits in the deck, 52 cards total. So 52 divided by 4 gives you the 13. So that's how I know I'm starting off with a total of 13 cards that are diamonds. And then I subtract from there. All right, let me look at the questions here.
So quick question. Every time multiple events occur, we always want to remove one from the deck or remove one choice option from the starting.
Not necessarily. Multiple events mean multiplication. We're removing a card from the deck from the starting because it said without replacement. Right. So because the original instruction said, well, words to the effect of, oh, it says it right there. The first card is not replaced before the second is drawn. That's why we reduce. But if it didn't say that, or maybe it flat out said that all the cards are put back in the deck before the second card is selected, then our second probability would be unimpacted by the first probability, and we'd still have a 13/52 in both cases.
Okay, that's clear. Thank you.
Okay, and so the good news, so it's good news, bad news. So we're kind of duking it out with the notation here, but there is a little payoff for it at the end. Because when you look at it, we're talking about kind of an implied or situation, because if I'm only taking 2 cards out of a deck, I'm not going to be taking out 2 diamonds and then 2 hearts and then 2 spades and then 2 clubs. That's total 8 cards. All right, so that's not going to fly. So it must be an or situation. Right, so we have an and an or combo. Now the good news is, so that's the quote unquote bad news. But the good news is that the probabilities aren't going to be any different for the other ones, because even if I write it out as, let me just try to keep the color scheme here consistent, probability of getting a heart multiplied by the probability of getting a heart after I already got a heart. Well, if I shuffle up the deck, all the cards are right back in. I'm back to square one. Select a card at random from the deck. There's 13 hearts, just like there were 13 diamonds out of 52. Once I remove one from the deck, specifically a heart, because we always assume success, that's going to put me at 12 out of 51 for my second selection. Right? So what we're looking at here is the fact that we're going to get 4 probabilities that are exactly the same, because there's no reason to think that it's going to be any different for the spades or the clubs. So a little shortcut would be to say, all right, well, if you know the outcomes are going to be the same for each trial, then why not just figure out the probability for one of those trials and then multiply the result by 4? Right? So you could do that, or you can just add these values up against themselves and you'll see what you get as a result. Right? So multiplying across the top here, we'd be looking at 156 over 2652. And again, there's 4 of them. So what I would do is I would just take that and multiply it by 4. All right, so I could just chuck it in over here. Actually, this is all from last class. I don't even need this. Not our last class. My last class is last class. So 13 52 multiplied by 12 out of 51. And then, it reduces it, but that's the same as 156 out of 2652. You can go with the simplified form or otherwise. So if you go with the simplified form, so well, I don't want to skip too many steps here. This is the same as saying 1/17 multiplied by 4 would give you 4/17. And then you can't, well, I would say that you can't always look at a final answer for probability and say, well, that makes sense based off my personal experience, but sometimes you can. And if you can, then you probably should. The other possible acceptable answer would be 624 out of 2652. So if we kind of look at this using personal experience, so I'm just going to throw an or here. Either one would have been okay. If we use a little bit of personal experience, we can kind of at least get an idea of whether or not these answers make any kind of sense. And so we got two cards of the same suit. Each one of those pairing of cards, or I'm sorry, each type of card amounts to a quarter of the deck. So if I want to get two consecutive cards, it's really saying I got roughly a 1 in 4 chance of that happening. It's like, it's one of those kind of situations where it's like, well, how would I know that? Well, if you have experience playing cards, then you'd look at it and say, well, yeah, that feels right. If you don't have experience with cards, then that it doesn't help you. But you will come across some instances when dealing with probability where you're like, oh, that reminds me of the time where blah, 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 like whatever happened. And you'll say, oh, that's why that happened. So whether it's a lottery or something along those lines, but it does give you kind of a feel for how things play out. In poker, an application of this, it's a simple application, but and it wouldn't involve the entire deck of cards. But when you play 5-card poker, after you get your hand, you lay down some wagers, you look at your hand of cards and you say, oh, okay, I don't want these two. These two don't really help, make a full house or a 2-pair or something like that, or a flush. Maybe I'm going for a flush. Maybe I have 3. In this case, that would actually make sense. Maybe I have 3 clubs and the other 2 aren't clubs. So I'll toss those 2 and I'll pick up 2 fresh ones, hoping that those are clubs. But maybe I won't make that decision if I don't think the probability of picking up 2 clubs is going to be that good, because I know, I don't know what everybody else's cards are, but I know that, let's say I'm playing against 4 other people. I know 20 cards are out of play already. Right? But for, 20 cards, because the 4 people, 5 cards will pop. And I already have 3 of the clubs. So, I can't speak to what the cards would be in the possession of the other individuals, but I know that the deck is already down really 25 cards if you include your own cards. So you're down into the 20s, 27 cards, and 3 of the cards that are clubs are already off the table. They're already out of the deck, so you only have 10 to work with. So now you're looking at 10 available cards that you would want, if assuming that none of the other players got any of the clubs out of 27 overall. So then you could look at it and say, okay, 10 over 27 and then 9 over 26. And you look at your probabilities and you say, oh, okay, well, it's worth going for it, or it's not worth going for it. You need the exact values in those instances? No, you just need a feel for it. That's really what I'm getting at with this. So for number 4, 2 cards with the same value. So now I'm looking at it like, all right, maybe I'm, same idea playing poker. Maybe I'm working on a full house. I want you know, I got a pair already, and I have, let's say, an ace, you know, and I'm looking to get a 3 of a kind with the aces. I'd like to see what the probability is of getting those 2 aces, you know, but here it's a little bit more general, 2 cards of the same value, because worst case scenario, maybe I don't pick up 2 aces. Maybe I just pick up 2 cards of the same value, in which case I have 2 pair, right? So that's something to keep in mind. But if they're going to have the same value, you're looking at cards like a 2 and a 2, a 3 and a 3, a 4 and a 4, and so on. 5 and a 5, 6 and a 6, 7 and a 7, 8 and a 8, 9 and a 9, 10 and a 10, jack and a jack, queen and a queen, king and a king, ace and an ace. All right, go all the way to ace and an ace. This is 13 possible pairings. All right, and I'm not looking for the probability of all of them happening simultaneously. I'm looking for the, you know, any one of these to happen, but I have to account for any of them happening. All right, but it's still the same general theory as the previous problem, where I look at it and say, okay, well, how many 2s do I have in a deck? I got 4 of those out of 52. All right. If I'm going to have a second 2 and I haven't replaced the first 2 before I made my second selection, then I'm looking at only 3 remaining 2s out of 51 cards remaining in total. So I'm cutting out a lot of the notation here just to get at the, you know, the number crunching. But I'm looking at 12 over 2652 just for that one computation. So then what you would just ask yourself is there any reason to think that the rest of the computations would be any different? All right, 3 and a 3, for example. Well, there's 4 3s. If I start over, shuffle the deck up again, there's 4 3s. If I select one of them, then I'm down to 3 3s, 51 cards overall, still going to be 12 out of 2652. Since I have the 13 possible pairings, I can just take this fraction and multiply it by 13, and I'll get my answer of 156 over 2652. Right? So I wanted to take an opportunity in doing this problem to show you just how streamlined you can make this process, because going through the last one, I made it seem like, oh, these problems are going to take you forever, but that was because the emphasis was on the notation.
Did that last step change the result at all, where you multiply it by 13? Because no matter what, you're going to draw a value, and then it's really a question of whether you draw the same value, correct? Could you just eliminate that last step?
Right. Well, you'd have to, if you were going to do it using what you're suggesting, then you wouldn't start with the 4 out of 52. You'd be starting with 13 out of 52, because any of the values 2, 3, 4, all the way to ace could be the first value that you selected.
Oh, okay, got it.
Right, and then the second one would have to be the one that's the same as the first one that you selected. So either way, it would come out to the same answer, but it would take a different approach.
So, Professor, question.
Sure.
Why you use the 13? Because of the 13 possible pairs?
Exactly.
Okay.
I guess one follow-up, and start to hammer on this again. It's just, you're right that yes, it's 13 possible cards, but I guess at that point, isn't it a 100% possibility that you draw a card, and then it's a question of just the second one that comes after it? Like you're gonna get a value, and at that point you don't know if it's going to be
right. But then you have to account for the probability of getting the same value, right? Which
would be the 3 over 51, correct?
Well, that would allow for any 3 values, even if it's not the same as the one that you selected, to be the second card selected. So you'd have to pin it down so that it was precisely the same card that was selected. So you'd have to be looking at, I'll just jot it down here. It would be probability
Mhm.
of anything from 2 through ace. And then same card, just shorthand notation.
Yeah.
So any card 2 through ace. So you could say the 52 out of 52 for that.
Mhm.
But then once you, oh, I understand what you're saying now. Okay, yeah. So then, for example, if it's, I was misunderstanding. I thought you were talking about.
I guess it's like given a deck and it's literally just drawing 2 cards from a deck and I don't know which 2 values, will I get 2 identical values?
Right.
And
So
I'm not specifying I'm going to get 2 2s, 2 3s, etc. I'm just, will I get 2
values that are the same, yeah.
Draw.
Which essentially is the question. But yeah, it would be, you're right, it would be 3 out of 52. Sorry, 3 out of 51, as you said, which would give you the 156 out of 2652. Yeah, because for example, if that first card is
Oh, so that actually got to the same thing that you
yeah.
did. Cool.
So if the first card is a 10, for example,
Mm-hmm.
then we assume success.
Actually, didn't realize it would resolve that cleanly. I was just curious.
Now there is only 3 10s and 51 overall.
I'm sorry, could you scroll down just a tiny bit? I can't see the.
Yeah.
Mm-hmm.
Yeah, so if the first card is a 10, for example, we assume success. Now there's only 3 10s and 51 overall. So then the product, and that's it.
First card is X, and then you have 3 of X remaining to draw on your second card.
Exactamundo.
So all fours amount to the same. So you just multiply the 156 to 652 by 4. I'm sorry.
For this one, you wouldn't have to multiply it by 4.
Mm-hmm.
Because that the 4 cards has already been accounted for in the process already.
Okay.
So we don't have to worry about that part of it, because the fact that 4 cards were selected, or 4 possible cards could have been selected, that was already accounted for. So we're in good shape there. And we don't have to worry about suits, because, and that's the only reason why you would multiply by 4, because there was no condition that it needed to be like a 2 of hearts or a 2 of diamonds or anything like that. So we don't have to worry about that either.
Okay.
This is an or, because this is another approach that you could use for that problem.
Yeah, it was just how I interpreted that question in particular. Any 2 cards that I need a pair. It's not a X, it's just a pair.
Yeah, it's a good observation.
Cool, thank you.
So let's hop on over to the next page. We're talking about the general multiplication rule, and this is the last thing we'll talk about for tonight. It's like a fair amount of space to do these kind of problems, but it's actually going to boil down to a very straightforward concept. But that straightforward concept has serious implications, if I can sound serious for a minute. It's an extension of the concepts associated with the multiplication rule, but what it does is it allows us to take advantage of what I was saying before, where if I tell you that you're looking for a card that's not a 2 in a deck, I could say not 2, or I can list out every possible card that it could be. It could be a 3 or 4 or 5, all the way up to an ace. Right? So this technique allows us to take advantage of the idea of complements, right? It allows us to take advantage of the opposite of the event that you're looking to find. If finding the probability of the opposite of the given event is simpler than the given event itself, then there's an advantage to doing that, right? You won't see much of an advantage in the first couple of examples, but you'll see that in the ones afterwards, that it's like, whoa, okay, thank the maker that there's this option here, right? So the first example, find the probability of tossing at least one head in 2 tosses of a fair coin. Right, so 2 tosses of a fair coin. And I'll take you through the process first, and then I'll show you how you could have done it without using this process just to verify it. But using this idea, probability of at least one, now in this case, it's at least one head in 2 tosses of a fair coin. I'm just going to streamline that to at least one head, is equal to 1 minus the probability of no heads. All right. So if I look at, I'm just going to make a little table of values here. If I look at X as being the number of times that you can get heads, so let X you think about how many times that you can get heads when you flip a coin 2 times. It's possible that you didn't get any heads. All right, so no heads. It's possible that you only got one of them to be heads. And it's possible that maybe they were both heads. All right, so these are the possibilities that we're up against when it comes to flipping a coin. Now, imagine you're flipping a coin 10 times. It's possible that you got no heads, 1 head, 2 head, 3 heads, 4 heads, all the way up to 10 heads. That's a longer list, right? We eventually would need to figure out the probability of each of these outcomes occurring. And that list of probabilities is what's known as a probability distribution, but we're going to talk more about that next class. So what's happening here is the idea that there's got, and when you're thinking about probability, if you have the mentality of there's got to be an easier way, I can't promise it's always going to work, but it'll get you thinking, all right, I can do it this way. It's going to take me 1.5 pages to solve it out. Or if I think there's got to be an easier way, take a moment and think about it. Maybe you come up with something, right? In this case, if we take into account, I don't know why that happened. If we take into account the fact that all these amount to all the possible outcomes that we could have if we flip a coin, then the total probability here would have to be equal to 1, right? Because whenever you account for everything in a set, in an entire sample space, you account for everything, that's a total probability equal to 1, right? So what this idea is telling me is that, yeah, I want to find the probability of getting at least 1 heads, which is, according to this, 2 computations. I would need to figure out these 2, right? I'd have to figure out the probability of getting 1 heads and then 2 heads and then add them together, right? So, and I'll show you in a tree diagram in a couple of minutes what that amounts to. The alternative is find the probability of the thing that you don't want, all right? So this is the one outcome that we don't want. So find that probability, and then collectively, if we subtract that value from 1, then the result will be collectively all the other probabilities, right? So what I'm going to do here is I'm going to say in 2 tosses of a coin, the probability of getting no heads. Let's use H for heads. All right. So 2 tosses of a coin, probability of getting no heads. Well, taking that moment to think about it, that must mean that we're dealing with 2 tails. I got tails and then another tails. Right? So probability of getting tails multiplied by the probability of getting tails. All right? I don't have to worry about the given here, that given line, given that the previous event already occurred. And the reason why is when you flip a coin, it doesn't matter how many times you flip it, the probability of getting heads is always 1 out of 2, assuming a fair coin, and the probability of getting tails is always 1 out of 2, right? So it's never going to be impacted by the fact that you already got a tails. Like I can flip a coin 30 times, the first 29 times, all tails. The probability of getting tails on the 30th attempt is still going to be 1 out of 2. Right? So it doesn't make a difference how many trials there are. So in this case, I'm looking at 1 out of 2 multiplied by 1 out of 2, result 1 out of 4. Right? So that amounts to the probability that I don't want. Right? We don't want this one. It's like being on an interview. You know, like when they say, you know, let me ask you, what are some of your weaknesses? And then you say, well, my weakness is I try too hard. You know, like you didn't tell them a weakness, you told them a strength. You just framed it as a weakness. You know, and so it's the same idea here. We're not answering the question that we're being asked. We're answering the opposite of it, right? So what we just figured out is the probability of getting no heads. If I subtract that from 1, right? So 1 minus, and again, that 1 is coming from this guy over here, the fact that the total probability has to be equal to 1. If I subtract from 1, the probability that I don't want, and I'll get the probability that I do want, of the event that I do want. So 3 out of 4. Now, this is a small sample. You know, we're only flipping a coin twice. So could you have done it a different way? Absolutely. You know, that different way could be a tree diagram. So coin 1, heads or tails. Coin 2, I flip the first coin and I get a heads, I can still get heads or tails on the second coin. If I flip the first coin and I get a tails, I could still get heads or tails on the second, heads or tails on the second coin, right? So this is my sample space, my tree diagram. If I want to know any instance in which I get a head somewhere in that distribution, doesn't have to be for both coins, just has to happen at least once, then what I would do is I'd just go down the pathways and I'd say, okay, well, any one of these is going to involve a head, and also this one. The one that doesn't involve a head would be the last one, right? So what I'm looking at is I got a heads here, in this pathway, but not that pathway, right? And so that leaves me with a probability of at least 1 heads, equal to 3 out of 4. All right, so we could do it that way, but then you see in the next one, we're flipping a coin 3 times. That's going to make a bigger tree diagram. Still within the realm of, you know, what we're capable of doing, but it's starting to get into that gray area of like, all right, there's got to be a better way, you know. So what I'll do here is I'll just do a quick copy paste. I always make a lot of friends when I do this. All right. The breakdown here is we're going to have 1 heads, 2 heads, but we could also have 3 heads. So I got to make some adjustments. All right, so it'd be the number of heads in 3 tosses. And again, in 3 tosses, if we're going to have no heads whatsoever, they would all have to be tails. Right, so it's the same general idea where we're determining a collective value, where we would say, all right, this is the thing that we don't want, but everything else is what we do want. Right, so this is what I'll do it in green. This is what we want. All right, the collective, the sum total of the probabilities for getting one head, two heads, and three heads, or three heads, sorry. And so if we find the probability of the thing that we don't want, which would be 1/8, because it's just including another coin there, then subtracting that from 1 would give us the probability of the thing that we do want, which would be 7/8. And that's the probability of getting at least one heads. And it would be verified by drawing out the full-blown tree diagram. But, and again, it's not too crazy, but it would be pretty crazy for something like number 3, where you'd say, okay, well, wait a minute, there's got to be a way to do this that's even easier, because I don't have to draw this diagram every single time. So it's still the same general idea. Less copying and pasting now. It's 37 tosses of a fair coin. Obviously not drawing that tree diagram. I don't even want to draw the table. That would be something pretty crazy. Right? But if we think about it, getting no heads when we flipped a coin twice, that was 1/2 times 1/2. No heads when we flipped a coin 3 times, that was all tails. 1/2 times 1/2 times 1/2. So 3 of those 1/2s. So it's going to be the same idea, except we're going to have 37 of those 1/2. So we're still going to have a 1 minus. But instead of saying 1/2 times 1/2 times 1/2, I'm going to say 1/2 times 1/2 times 1/2 times 1/2 times 1/2 37 times, which would be the same as saying 1/2 to the 37th power. All right. Now here, you kind of run into the territory of like, we're probably going to get stuck with a decimal, but we'll see what Desmos has to say. All right. So 1/2 raised to the 37th power. All right. So, I mean, it's basically screaming 1, but it's not quite. Right. So it would be something that would round to 1, but we wouldn't say 1, because 1 would mean it's a certain event. If you flip a coin 37 times, it's not guaranteed that there's going to be a head in there, but you're feeling pretty good about your chances. Just getting 1. They don't all have to be heads. You're feeling good that at some point in the process, the head side of a coin is going to come up, right? And that's exhibited by the probability that we just came up with. But we would have to write this entire decimal out. So 9, 9, actually I lost track. I think it was 11 nines, 2, 3, 7, 8, 9, 10, 11 nines. And the reason why we'd have to write the whole decimal out is because there's really no way to round it, aside from the way I just rounded it, without it rounding up to a 1. And if I said round to the nearest 10th, or the nearest 100th, or the nearest 1000th, or whatever, it would round to a 1. And it's not equal to 1, because there's still, it's the 1 in a million thing from Dumb and Dumber. There's always a chance. You're saying there's a chance. It's a very minute chance that you flip a coin 37 times and you don't get a single point with the 2724 at the end for a more exact value. there is that little minuscule chance that you can get all tails, but it's so minuscule that it's almost negligible, but it is still possible. So we have to account for that as a possibility. All right. So what I'll do is I'll put a little star on number 4. Let you try that one for homework. And then we'll get on to conditional probability. I lost track of what I'm going to be teaching next, so I just took a quick look. Conditional probability, which is not difficult, at least the way I teach it. And so so that should be something to look forward to rather than something to be dreaded. So so we'll leave it here for tonight. If you have any questions, stick around. Otherwise, have a wonderful evening, and I'll see you on Monday.
Thanks, Professor.
Thank you.
Have a good night.